One extraordinary group of animals rivals us as masters of Earth. They ruled the ancient sea, and they were the first creatures to venture onto land.
The conquest of land really is one of the most important events in the history of life. It really was a landmark and a breakthrough.
With highly adaptable limbs and bodies, they invaded every realm of the planet, equipped by nature to survive almost any challenge. Their offspring would terrorize the inhabitants of fresh water. And overcoming unimaginable obstacles, they would even take to the air and spread across Earth as conquerors.
They're found in every habitat. If all of them were to vanish, all life on Earth would also vanish.
Who were these relentless invaders, and what led to their extraordinary success? Success we now try to imitate.
Thank you, baby.
Join us as we travel back in time to understand the most diverse group of animals that has ever lived on Earth. Earth, 500 million years ago, long before the first dinosaur has appeared. At that time, the land surface, swept by extreme temperatures, is so inhospitable that no animals or plants could survive here. The only animals on Earth dwell in the nurturing womb of the sea, where all life began. Many species of this period are bizarre, almost alien. Among them, one group of animals will find a way to leave this watery home. But who were the creatures that made the very first steps onto land? Their identity has long been one of the great mysteries of science. Clues that could identify the first animals on land have turned up in some surprising places. The village of Sennybridge, nestled in the Welsh countryside of the United Kingdom. Scientists are drawn to this pastoral landscape because hidden beneath it are telltale traces left by some of the first marine animals venturing onto land. Fossil evidence that could help reveal their identity.
Okay, let's take a look down here.
On this rocky outcrop, paleontologist Simon Brady looks for a snapshot of the early world.
Ah, look what we got here.
That's really fun.
One of the wonderful things about the science that I study is that it really is a science of discovery. I love the thrill of the chase, the idea that there is a fossil somewhere out there that may be able to completely revolutionize our view of the evolution of life.
Frozen in time, fossilized bodies have long provided our best window into the ancient world and its inhabitants. If an animal died in the right place and under the right set of conditions, its preserved body could gradually fuse into the surrounding rock. It could leave its mark on the world across millions of years. But Brady is not looking for dead bodies. He seeks marks left by living animals as they were invading the land. Eons ago, pioneering animals crept from the watery realm onto the new world of dry land, leaving their footprints. In some places, their tracks were preserved, perhaps by a sudden covering of volcanic ash or a landslide. Brady hunts for these tantalizing traces of ancient creatures in this rugged countryside.
I find it fascinating to study the trackways of these animals because they represent these paleopolaroids or snapshots in time. You get a real feeling of the activities of these animals. It really does impress upon you the fact that these were living animals.
Brady and his colleague discover evidence of an animal invasion along an early shoreline.
The problem with trackways like these is that sometimes it can be difficult to see the actual tracks. But if you rub muddy water over the surface, sometimes it can help to bring out the tracks.
Though they appear small to us now, the first footprints on land were made by a giant of the time. Like a detective, Brady must now decipher the clues he's gathered to find out who created these trails. Not far from the fossil site, Brady's search continues at the University of Bristol. Here, he probes the past, not in soil or rock, but in a basement crypt. These drawers contain tons of trackway specimens collected from around the world. Amid this overwhelming mass of fossils, he has found a pattern, revealing a secret critical to the success of the first animal on land. It walked on legs. Legs may seem mundane to us today, but Brady wonders who first developed this radical design.
Sometimes I find myself drifting off back in time 400 million years just to try and envisage what it must have been like when these trackways were being made.
To determine which animal could leave trackways, Brady surveys the possible suspects in the ancient sea. Cnidarians were the first animals to have muscles and a nervous system, and they may have been the first to actually move on their own. But they never found a way to move out of the water. Ancestors of this flatworm were the first animals with heads, primitive brains, and stereo senses. Flatworms can glide along a mucus carpet, leaving a slimy trail, but they don't have legs. The group called mollusks dwells both in the sea and on land today. But they move on a single foot, which doesn't leave trackways like those Brady studies. Of all the creatures present in the ancient sea, only one group had legs capable of making the fossilized tracks. They're called arthropods. And one of the secrets of their success, jointed legs. Legs which can bend about a hinged joint provide great stability and shock absorption. Perfect features for an all-terrain vehicle. With their many joints, each leg has tremendous flexibility. Tendons attached to powerful muscles produce a range of motion. To help guide them through their world, arthropods developed a package of onboard sensors, appendages like antennas, and the first complex eyes capable of perceiving sharp images. But most importantly, their legs and body segments could easily adapt to almost any new opportunity. A small evolutionary push turns a walking leg into a grasping claw. Take the segmented swimming tail of the lobster, tuck it underneath, and you've got a sand-burrowing crab. The basic arthropod body plan, with segments and legs, packs an incredible potential to adapt and evolve. As a result, there are more arthropods in the world's oceans than any other group. And each species is a variation on the same arthropod theme.
Arthropods are successful because they have a very simple type of body plan that is easily adaptable. They have various series of different legs which can be easily adapted for food gathering, feeding, or for locomotion.
Their seemingly countless appendages were deployed in many revolutionary ways. But it was just a matter of time until the right toolkit came along with which they could conquer the land. The arthropods' dominance of the sea was greatly aided by one of the most important aspects of their body plan: their skeleton. An arthropod wears its skeleton outside its body. This hard shell serves not only as support, but as body armor, shielding its soft inner organs from harm. There are times, however, when an arthropod must leave its armor behind. In order to grow, it undergoes one of the most amazing transformations in the animal kingdom. First, the mounting pressures of its growing body crack open its exoskeleton. Beneath the shell, a soft, new skeleton has been developing. In less than 30 minutes of struggling and squirming, this crab breaks free of its old skeleton, a process called molting. It emerges with an entirely new covering, from legs to body to eyes. Its soft new skeleton will inflate quickly to a larger shell and harden during the next 2 days. For the soft shell crab, a prized meal of many predators and humans, it's a dangerous 2 days. Yet when the shell hardens, their appendages strengthen, and uniquely sophisticated tools for exploiting every opportunity are ready for action. They are highly versatile and vigorous eaters. While their claws tear into a dead fish, their mouth appendages whirl in a flurry of activity. Some help with eating, some with breathing, as they sweep water across the gills. And they are not afraid to use their claws to take on members of their own species if a meal is at stake. Watching a standoff between blue crabs, it's not hard to imagine a prehistoric time when heavily armored arthropods first sparred over food. Arthropods arose and thrived in an ancient era when life was diversifying explosively. And they succeeded across time in an arms race of size and strength. One of the very early arthropods, Anomalocaris, was also the most savage and fierce predator in the prehistoric sea. It captured prey with powerful appendages, then quickly devoured its victim with razor-edged teeth. But Anomalocaris was later dwarfed by an arthropod that was the real stuff of nightmares. When paleontologists gather, that monster, called a Eurypterid, is the source of lively debate.
Cheers, everyone. The Eurypterids, or otherwise known as sea scorpions, were a group of giant predatory arthropods.
No, I'm not. Well, one thing I always say is that I'd much rather be in a swimming pool with a 6-foot shark than a 6-foot Eurypterid.
You're kidding.
I don't know. No, I'm quite sure. They had specialised serrated teeth, which would have been very good at cutting through flesh and bone, and in a few simple movements it would have been able to sever your arm.
They had the mechanical strength to do that?
I would think so, yeah.
So you see it strongly in terms of competitiveness?
Eurypterids could grow as long as 6 feet. With powerful swimming appendages and extremely fast claws, they could be ruthless hunters. A Eurypterid might sometimes have to fight for its meals against another giant. The outcome of this prehistoric battle between claw and tentacle will always be a mystery. There is a relative of the now extinct Eurypterids still dwelling in the sea. Beneath its helmet-like shell, the horseshoe crab is hardly ferocious. But one aspect of its behavior today may explain why marine creatures first stepped out of the sea long ago. Horseshoe crabs find their mates in the water, but then they journey to the edge of the ocean. These living fossils leave the sea briefly, like a landing army, to lay their eggs beyond the water on a beach. Protected from the harsh environment by moist sand, their sealed eggs actually develop on land. Brady proposes that the first land excursions may have looked much like this, as some Eurypterids sought to protect their eggs from ocean predators. And they left plenty of indirect evidence in the form of trackways. This trail was left by an ancient relative of the horseshoe crab, perhaps, Brady imagines, seeking a safe site for its eggs. But like this juvenile horseshoe crab, it could not have stayed long in the world of air. Many early arthropods breathed as horseshoe crabs do through thin, page-like structures called book gills, which only work in water. Unable to extract oxygen from air, this line of arthropods was consigned to a life beneath the waves. But other arthropods would not be stopped, and new blueprints were already in the works. Consider the enormous challenges sea creatures face in migrating onto land, even if they somehow find a way to breathe air. Biologist Bill Shear is obsessed with figuring out how they did it. Combining a knowledge of modern arthropods and the ancient Earth, Shear tries to identify the tools needed to make the transition to land.
It's hot, it's very dry, There's very intense sunlight, which means intense ultraviolet light. There's no buoyancy supporting the body, so the full force of gravity is felt by any organism in the terrestrial environment.
But early arthropods already had equipment with great potential to overcome such obstacles. Scheer believes that their exoskeletons evolved new adaptations to seal out the harsh, dry world of land. And their multiple appendages developed into more tools than we could ever imagine.
These limbs are almost infinitely modifiable. They're like the many blades of a Swiss army knife.
Those that left the sea could invent a whole toolkit with which to conquer the land. Tasting, sensing, grasping, and finally winging their way to dominance. But how did they initially survive that perilous step from the sheltering ocean to the treacherous conditions of land? Scheer suspects they discovered a special bridge between land and sea, one that still exists. The historic bridge permitting the conquest of land may have been nothing more elegant than simple algae scum. Long a food source and home for aquatic dwellers, these mats grew along shorelines and above the water's edge on land. Perhaps they served like base camps, providing food and habitat to launch the invaders into the terrestrial world.
Under those mats, conditions were tempered, and that gave them the time they needed to develop the new adaptations that would take them fully onto the land.
The first animals here were tiny, much smaller than the Eurypterids. So diminutive, in fact, that the evidence of their journey was long overlooked. Much of this chapter of the invasion story was completely unknown until recently, when a surprising piece of evidence came along that changed everything. A secret was uncovered in the fossil remains of early plants, which were spreading onto the continents. Within the plants, researchers found what they thought could be the microscopic remains of ancient arthropods. At first, their discoveries were dismissed. But with these new clues, an expert in arthropod anatomy like Bill Scheer would be able to rewrite major chapters in the Book of Life. To get to this evidence, Scheer would have to extract microfossils from solid rock. He used hydrofluoric acid to dissolve away the rock and leave behind only the organic fragments it contained, the remains of plants and animals. His discovery would forever change our view of the arthropod colonization of early Earth.
When I came in the next day and washed and filtered the sample and found animal remains in it, it was wonderful. I can remember seeing some of the really striking fossils for the first time. You just get a feeling of excitement that's probably very similar to scoring the big touchdown at homecoming, in the homecoming game. You just feel on top of the world, and it makes it worth all of the tedious searching and work that leads up to that.
Scheer now had the remains of the little invaders, but they were only fossil fragments. In order to see an entire animal, he would have to reconstruct them piece by piece. It was like assembling the pieces of a jigsaw puzzle without benefit of the picture on the box. One of the first creatures unveiled, an early ground-living spider. One success led to others. Gradually, Scheer identified an array of early land colonists. His work with the microfossils confirmed what was long suspected. Many different kinds of arthropods were invading the land at the same time. In Scheer's mind's eye, the world of 380 million years ago was beginning to come into focus.
The world of the Devonian was probably different from our world in many, many aspects. The year was shorter, and the days were not 24-hour days. You'd have a different atmospheric composition.
Scheer believes that of all the likely suspects, the very first pioneers to overcome the new conditions, the first land conquerors, took to the land like the little pill bugs of today. The first animal had arrived on land. Tiny lichens and lush plants had created the right conditions to open a new frontier for life.
The plant life would look quite different, strikingly different.
Just a few species of plants growing very densely, and these plants would look quite primitive.
The ancient plants may have looked different, but like their modern equivalents, they created microclimates that rendered the terrestrial world more hospitable. And there turned out to be advantages to living on land. There's more oxygen in air than in seawater. The arthropods just had to find a way to extract it.
The ancestors of scorpions, like the horseshoe crabs, probably had what were called book gills. And this was just a series of flaps arranged on the underside of the animal's body that were kept in constant motion.
Through the process of evolution, these flaps that worked well in water were relocated inside the scorpion. There, oxygen from air could transfer directly to the blood. Yet again, the arthropod body plan proved its versatility, adapting an old body part to conquer a new ecological niche. Over time, arthropods invented many different breathing techniques. In a separate land invasion, ancestors of the millipede developed a special respiratory system to supply their long, segmented bodies with oxygen. On the underside of its body begins a series of reinforced tubes, adapted from the exoskeleton itself. These tubes open directly to the outside air and draw oxygen into their bodies. A similar type of turbocharged system would play a key role in future arthropod conquests. Now that they could breathe, the conquerors moved inland for the first time. Though plant life was abundant, in this early world there was little variety, and the plants here were a lot harder to digest than algae. But while living land plants didn't offer easy nourishment, decaying plants and dead arthropods were a different matter. Dead material, broken down by bacteria and fungi, detritus, was a lot easier to digest. Over a few million years, the invasions produced a thriving community of arthropods adapted to life on land as detritivores.
The detritivores would have been among the earliest animals to come ashore by a number of routes. In addition to the detritivores, there were also carnivores, predators like this spider.
Long before weaving webs to trap prey, ancient spiders aggressively pursued anything that moved. As they spread successfully across the land, arthropods encountered rich hunting grounds submerged below water, fresh water. Those early water invaders included forerunners of modern arthropods, such as insect larvae, ferocious pond predators exquisitely adapted to life in fresh water. Stalking its prey much like a cat, a dragonfly larva. The newt is among its victims. The dragonfly larva pumps water over its gills. When it needs to move quickly, it uses the pump for jet propulsion. In this pond, even predators have to watch their backs. But freshwater predation is literally child's play for this dragonfly and some of its arthropod cousins. It is about to move into the adult stage of life. When a predatory larva prepares to leave the pond, it reenacts a pivotal moment in the story of life. Through metamorphosis, it turns not only into an adult, but into an animal capable of entering yet another realm of Earth. A damselfly larva emerges from its freshwater exoskeleton, discarding the tools it used so successfully in the pond. Hidden beneath its underwater coat is a new tool that will define its life outside the pond. a set of appendages capable of miracles. When arthropods developed wings, animals flew for the first time. Dragonflies are little changed from the fossil record. Striving against the pull of gravity, they live graceful lives on the wing. Hovering, making effortless acrobatic turns, they are unparalleled aerial hunters. They even mate in the air. As the male protects her from above, the female carefully deposits her eggs into the pond. Each dragonfly species has a slightly different mating flight. Even during this delicate pairing, males fight battles for territory. In dragonflies, the arthropod body plan demonstrates its supreme adaptability, a single animal that dominates both water and air in different phases of its life.
Since the invention of flight by insects probably allowed for their enormous diversification, I would say that the invention of flight by insects was one of the most important events in the history of the Earth.
The insect wing is an engineering marvel. It's reinforced by stiff supporting veins, which are thickest where the wing's leading edge slices through the air. Flight turned out to be such an effective adaptation that today, more than 3/4 of all the animal species in the world are flying insects. Flying enabled insects to explore and to conquer every corner of the terrestrial world. Arthropods had risen from the sea of their birth into the air. But the arms race between hunters and the hunted also moved into the air. The miracle of flight did not protect insects from their enemies. Another arthropod, the spider, developed a gossamer net to catch prey on the wing. We are surrounded by hordes of crawling, running, scuttling, and flying arthropods. These little creatures shape the face of the world for all of us. In fact, we couldn't live without them.
Insects have been called the little things that run the world, and this is really true. Without insects, most of our ecosystems would simply collapse.
Insects provide essential services that keep the machinery of life running, including a role as nature's recyclers. They preside like undertakers over the grim passing of life. But they also play a vital role in the birth of some of the most beautiful living things on Earth. Arthropods are drawn to flowers, the showy reproductive billboards of plants and trees. As they dine on tasty nectar, their bodies pick up pollen, which will be carried to other flowers. Acting as a pollen delivery service, insects provide flowering plants with an efficient way to reproduce and multiply. In turn, countless insects earn their living from flowering plants. Without insects, many familiar foods would cease to exist. Arthropods conquered the sea, the land, and the air. Much of the beauty and grandeur around us is due to their success.
Imagining life without arthropods is almost an impossible task because they are so intimately involved in virtually every aspect of life on Earth. Arthropods are found in every habitat. There are arthropods that are adapted to live in hot springs near boiling. They're found on the tops of the highest mountains. They're found at the bottom of the deepest trenches in the sea. This is truly an arthropod planet.
Arthropods have invented ways to live in harsh places that we can visit only briefly. What enables them to thrive in places where we are hard-pressed to survive unaided? In a land of permanent winter, they flourish beneath thrashing floes of Arctic ice, and the cold sea provides a rich bounty as a result of their presence. In one of the Earth's most extreme environments, along the ocean's deep trenches, crabs prosper amidst toxic hydrothermal vents. Could we somehow learn from the arthropod blueprint how to better explore extreme parts of our planet? Today, scientists are trying to unlock the secrets of arthropod success. At the University of California at Berkeley, scientist Bob Full runs a lab devoted to understanding every aspect of arthropod locomotion. The ease with which they move about the world is clearly a key factor in their success. Full probes the reasons why they are so good at traversing the Earth.
Really, I'm interested in their movement, so you can discover the secrets of how their muscles and their skeletons work to allow them to move so wonderfully in the environment.
Arthropods are built low to the ground, an inherently stable design. Studied at slow speeds, their movement reveals a telling pattern.
When we looked at arthropod locomotion, we saw that they function in general like a tripod or a stool. 3 legs are on the ground at once, and as a result, they're incredibly stable.
Yet most arthropods need to move extremely fast. Full discovered that speed is possible because their walk doesn't require much brain power.
We typically think that control of locomotion comes from your brain. In fact, without any brain at all or any reflexes, the animal can self-stabilize by using this wonderful skeleton, because the skeleton can act as a spring and a shock absorber, greatly simplifying the control.
But Full has found that jointed legs seem to be the essential marvel of arthropod design.
They actually can act as springs and struts and shock absorbers to keep the animal stable so that it's able to use its power to move forward in the environment.
Full's lab has dissected the arthropod body plan for the secrets of its strength and resilience. They've discovered that the best way to move over the surface of the Earth is the arthropod way. One day soon, humans may put the arthropod body to work in robotic probes and explorers. Physicist Mark Tilden was trying to build walking machines that could traverse complex terrain. They turned out to resemble arthropods.
The interesting thing about these type of designs is that they're efficient, contained, mechanically very simple, and they last for a long time. Arthropods are essentially the optimal mechanical design for this planet.
Simple arthropod-like walking machines such as this have spawned more elaborate variations. Some of these other prototypes are at the cutting edge of technology. Ed Williams is the chief technician for the robot Ariel.
Ariel represents a first step in coming up with a robot that's as sophisticated as an arthropod. One of the advantages of being an arthropod, or a robot modeled on an arthropod, is having jointed legs so that you can negotiate a much rougher terrain than you can with wheels or tracks.
When it comes to building a machine for locomotion, Ed believes we must admit that the arthropods have us beat.
Arthropods are so good at scrambling around an environment that's so rough, and they can do it so fast that it's currently just can't be duplicated by anything else. The original inspiration for Ariel was biological. She was patterned after a crab. She has 6 legs where a crab has 10, but she walks sideways on her legs like a crab does rather than forward on 6 legs like an insect does.
Thank you, baby.
Ariel is crab-like, but she has no natural instincts. She must be programmed to sense and interpret the world around her. And it takes all the power of her onboard computer just to move her legs in concert. Though she walks like a crab, Ariel lacks tools like claws, which enable crabs to manipulate their environment. None of our robot imitations can yet match even the simplest real arthropod. But like the very first arthropods in the primeval sea, Ariel may be on the verge of pioneering excursions into new realms. The supreme adaptability of her body plan may take her where few machines or people have gone. And she may help us peer into the greatest unknown region of Earth.
Well, the ocean is largely unexplored still. We know possibly more about the outer planets than we know about the depths of our own ocean. One of the problems with preserving the ocean is just simply getting enough information about the ocean from the remote places.
Craft like Ariel could easily get to the more remote places of the ocean and send back data that we currently can't afford to gather.
It would be such a boon to ocean research that it's just extremely exciting for us.
One day, we ourselves may use the incredible arthropod body plan to help us research and better understand our world. The long saga of arthropods is one of the great stories of life on Earth. Nearly 500 million years ago, they came to dominate the world's oceans, and they were the first of all creatures to climb onto land. The record of their invasions, etched in stone, is only now being deciphered and appreciated.
The conquest of land by the arthropods really is one of the most important events in the history of life.
They succeeded because their versatile bodies never stopped adapting as they pushed relentlessly into every habitat of Earth, even finding a way to overcome the pull of gravity and fly for the first time. Arthropods not only revolutionized life, but spread beauty and wonder wherever they went.
They fill every conceivable ecological role. So if all of the arthropods were to vanish, probably within a very short span of time, all life on Earth would also vanish.
Without them, the planet would be radically different. We owe an immeasurable debt to arthropods. These pioneers have filled our world with unrivaled diversity. We may think of ourselves as masters of the Earth, but given their achievements, it is clear that arthropods are truly the conquerors.